Okay, so we talked about publication bias, and on the y-axis of that plot we had effect size. So what is effect size? Well, if you recall, p-value was just the probability of, in repeated experiments, getting an effect of at least that size or more extreme. Okay, and so all it tells you is yes or no whether it was significant according to some threshold. It doesn't tell you how significant it was or how important it was. Okay, and that's what effect size tries to capture. So the effect size in a situation where you're comparing the means of experimental group and control group, then the effect size is the mean of the experimental group minus the mean of the control group divided by the standard deviation. And so this tells you not just significant, but how significant. And this measure is used prolifically in meta-analysis to combine results from multiple studies. And it's useful to help standardize across studies with different parameters, different sample sizes in particular, for example. Okay, and so in general, you got to be careful with this because average results from different experiments can produce nonsense if you sort of violate the assumptions under which the experiments were conducted. But it can be done. Okay, and so another caveat here is that there's other definitions of effect size exist. There's odds ratio and correlation coefficient, but we're just going to talk about this one. Okay, and so there's an argument here that the effect size should always be reported along with the p-value, even though this is very rarely done. And that argument is delivered by Robert Coe in this paper presented at the annual conference of the British Educational Research Association in 2002 that's cited here at the bottom of the slide. Okay, so a little more precisely, the effect size is the standardized mean difference where the group 1, the mean of group 1 minus the group 2 divided by, we said, the standard deviation. And here I'm writing this as the standard deviation sub-pooled. Okay, and there's lots of ways to compute a value for this notion of pooled. One simple way is just to take the standard deviation of the control group. And one by one argument here, hey, the variation is supposed to be the same because the sample, the two groups are drawn from the same population. Okay. Another way is to compute the actual pooled standard deviation, which is an expression that looks like this. And so we're not going to go into much more detail than that. But just to point out that the overall notion is pretty simple and that it's not unreasonable to use a straightforward definition of the standard deviation. Okay. So what's a big effect size? Well, because it is standardized, you can actually reason about what might be big and what might be small. So this is, again, one of these cases where it's sort of made up on the fly, but you can, one heuristic by Jacob Cohen is a small effect size is 0.2, a medium effect size is 0.5, and a large effect size is 0.8. So for, remember this is dividing by the standard deviation. So this is sort of for every bit of difference in mean, how much variance are you accounting for? Okay. And then finally, I'm not going to talk too much detail about confidence intervals, but I do want to mention that the confidence interval, the effect size, just to give you the intuition for this. So an advantage here is that these are maybe easier to interpret in terms of actual decision making. So what does a 95% confidence interval of the effect size mean? Well, it means that if we repeated the experiment 100 times, we expect that that interval would include this particular effect size measured in this experiment 95 out of 100 times. A corollary of this is that if that interval, if the 95% confidence interval includes 0.0, that's equivalent to saying that the result is not statistically significant. That means that 90% of the time that interval would include no effect whatsoever. Okay. And equivalently, if that interval does not include 0.0, then it is statistically significant. Fine. So that's some more terminology here. The other notion we mentioned in talking about publication bias was the idea of a meta-analysis. Okay, so this is looking back over previous studies and combining their results. And so in 1978, Glass sort of statistically aggregated the findings of 375 psychotherapy studies to disprove a claim that psychotherapy was useless. And this was the coining of the term meta-analysis. And this built on earlier ideas from other statisticians, including Fisher, who has this quote, when a number of quite independent tests of significance have been made, it sometimes happens that although few or none can be claimed individually as significant, the aggregate gives the impression that probabilities on the whole would be less likely to have been attained by chance. Okay, so this is individually look weak, but we can aggregate them to get a more powerful result. Okay, and so the reason I want to bring this up, this idea of meta-analysis, that it becomes even more important in the context of data science, because you'll often be working with data that you did not yourself collect. And so thinking of it as a meta-analysis experiment is potentially useful. And then another point is, that big data may have become big because it was combined from multiple different sources. And so understanding when this is okay to do and when this isn't is important. So how do we do this meta-analysis? Well, it's pretty simple. You just want to take a weighted average of the independent studies. Okay. And you want to give, so how do you want to define the weights? Well, you can define it different ways, but you want to give the weight to the more precise studies when possible, the ones that have more power. So a very simple method is just weight by the sample size, right? And so this expression here is the number in your group. So the weight for a group, for a study I, is the number of samples in study I over the sum of all the samples, the total sample size. A more sophisticated way is to use the inverse variance weight, which is 1 over the standard error squared. And I'm not going to give you the formula for standard error. You can look it up. But there's lots of variance here. The main idea is to understand why it's called inverse variance is that if the variance is very, very high on a study, you want to give that lower weight, right? That means it wasn't a very precise study. And this could be because the sample size was low, or it could be for other reasons. Okay, and the standard error is one common method of associating with the variance in this particular case. But again, it's important to understand the intuition rather than just memorizing the formulas. Okay, and then again, as usual, there's a caveat here. This is all for a fixed effect model. It assumes that every individual study is measuring the same true effect. And there's random effects models that help account for the fact when they may not be. And we're not going to talk about random effect models. Okay. So finally, one more term that was brought up in the context of publication bias was, well, sorry, I didn't bring up the term, but one more effect that you saw in the plot was this funnel plot, if you remember. The funnel plot was high variance on one side and it went to lower variance on the other. And so the general term for this that I just wanted to introduce you to is called heteroskedasticity. Okay, and so this is when the variance itself is not constant. All right, so here, as an example, the variance is high. The variance is high over here and low in the middle and high again over here. Now, this is not necessarily a problem. There are ways to correct for this, but it's not necessarily a problem because the estimates that you'll generate are still unbiased. Okay, but it can increase overall error estimates, leading to a reduction in statistical power, right? So you end up with this really high error numbers because all these guys count against you, right? Even though you're actually doing a pretty good job in predictions. So I should say how this plot was generated. This was again simulated data where I intentionally sort of varied the variance along the x-axis. Okay, so chose some x values and then sampled y values according to some distribution that varies in this way. And here I just took the exact same x values but repeated the sampling of the y values many, many, many times. So it gave me this clearer spread. But you can see these solid bars are because the same x values were used across all the experiments. Okay, and the point here is that drawing the regression line over and over again, it didn't change all that much. Okay. All right, we didn't get anything that looked like this, for example. Fine. So again, if the problem here is that you might increase the error and you might lose statistical power because it overlooks a real effect.